Welcome back. So, what we have learned is that if f is continuous at theta naught, then the Fourier series is Abel summable to f of theta naught. In other words, we have limit r goes to 1 a r f at theta naught. This is equal to, we know that a r f theta naught is nothing but f convolution with the Poisson kernel at theta naught, and this is equal to f of theta naught. Now, what happens if f is discontinuous? So, now we can address the issue if the nature of the discontinuity is a jump discontinuity. So, what is a jump discontinuity? Let us recall at, let us say theta, then limit h goes to 0, h greater than 0, f of theta plus h, this will exist and we will call that this is f of theta plus, and limit h goes to 0, h greater than 0, f of theta minus of h, this is equal to f of theta minus, this exists, and f of theta plus is not equal to f of theta minus. So, now let us assume let f be a 2 pi periodic Riemann integrable function. Assume f has a jump discontinuity at theta naught. So, then we would like to see a r f of theta naught minus of f of theta naught. As usual, we want to imitate the proof what we have done when when we proved a r f theta converges to f of theta if f is continuous at theta. Exactly, we will try the same fashion. So, if we write this, this is going to be minus pi to pi f of theta naught minus of theta and p r of theta d theta minus f of theta naught. So, what was our strategy? That we know that integral of minus pi to pi p r theta d theta is 2 pi. Therefore, 1 over 2 pi, that is we multiply by 1 and then we take club together f of theta naught minus theta minus of f of theta p r theta d theta. Now, if theta mod theta is very small, then we use the continuity of f, and then for the other thing what we have used is that integral over p r theta d theta, this goes to 0 as r goes to 1 away from 0. Now, here we have, as you can see, that there is certain problem here, because even if we are bringing it to close to f of theta naught minus theta minus f of theta naught, we do not have the continuity. So, we will have a problem for small theta. However, if I am approaching from the left, this is going to have a limit, I can pull that limit out. That means, if my theta is lying between minus pi to 0, then I have a chance to play the same game. Now, if my theta is positive, then if I am looking at 0 to pi theta, then theta is positive and less than some delta, then I can get it in the f of theta naught plus. So, that is what essentially we would like to play. Then my proposition if f has a jump discontinuity at theta naught, then limit r goes to 1 minus a r f at theta naught. This is equal to f of theta naught plus f of theta naught minus divided by 2. Okay. The proof already we have discussed, and for the sake of completeness, it is a good idea to write it again. So, observe P r of theta is equal to P r of minus of theta, and we have 1 over 2 pi minus pi to pi P r theta d theta, this is equal to 1. Therefore, what we get is that 1 by 2 pi minus pi to 0 P r of theta d theta is equal to 1 by 2, which is equal to 1 by 2 pi 0 to pi P r of theta d theta, because this is 1 by 2 pi minus 2 pi is the 2 times 0 to pi P r theta d theta, or minus 2 times minus pi to 0 P r theta d theta. So, that is easy to notice, and then if from here what we do is that a r f of theta naught minus of f of theta naught plus f of theta naught minus divided by 2 equal to pi to 0 f of theta naught minus theta P r theta d theta. Now, I will take only f of theta naught plus by 2 here. So, now this 1 by 2, now I can replace it by 1 by 2 pi minus pi to 0 P r of theta d theta, then plus 1 by 2 pi 0 to pi f of theta naught minus theta P r of theta d theta. So, this makes to minus pi to pi a r theta, that is what, and now we also have minus f naught by 2. So, this is again I will write 1 by 2 pi 0 to pi f of theta naught minus P r of theta d theta. Now, this what we notice is that it has a jump discontinuity, this limit exists. Therefore, for a given epsilon I can find a theta positive such that a delta positive such that f of theta naught plus theta minus f of theta naught is less than epsilon whenever mod theta is positive and less than delta. That means, let us rewrite it as f of theta naught plus exists. So, for epsilon positive there exists a delta greater than 0 such that whenever 0 is less than theta is less than delta, then f of theta naught plus theta minus of f of theta naught plus this is modulus is less than epsilon. So, you change it, this integral we have minus pi to 0 and plus 0 to pi. Then in this case you break this integral again exactly in the same manner when theta is less than delta, and here plus theta is greater than delta less than pi plus minus of delta is less than theta less than 0. This integral this is, and minus of pi is less than theta is lesser equal to minus of delta. So, this integral correspond to this 2 and this integral correspond to this. So, now exactly playing the same game we get that this is lesser equal to this, all things would be. Now, for at least we will do this one part. So, one part this is going to be lesser equal to epsilon, and then we have got p 1 by 2 factor 0 to pi and plus this is away from theta. So, when limit goes to r goes to 1, this goes to 0. So, hence so exactly I am not repeating the proof because we have already done the same thing, only here the idea is that on the right hand side the limit exists, on the left hand side limit exists. So, you break your function to f of theta naught by 2 plus f of theta naught by 2 and you play the same game in the interval minus pi to 0 and 0 to pi. So, what you are going to get is that this converges to the average of f of theta naught. In the similar fashion, one can show that if f has jump discontinuity at theta naught, then because again the fair kernel is an even kernel. So, we can play the same thing. So, we can say that it is Cesarosumable to f of theta plus minus by 2. So, if we have a jump discontinuity, it is going to converge Abel summable to the average of f of theta plus and f of theta minus. Same is also true for Cesarosumability. And now, it is natural to ask what about the summability of the Fourier series if we have a jump discontinuity. Can we say something about it? Okay. So, let us look at a concrete example where a function f what we have dealt with previously having a jump discontinuity. So, let us consider the function f of x, this is equal to pi minus of x by 2 if x belongs to 0 to 2 pi and is equal to 0 at x equal to 0. Now, what is this function? And then you extend to whole of R as a 2 pi periodic function. So, now suppose this is pi, this is our 2 pi, this is minus pi minus 2 pi, then here f of 0 is equal to 0, and if I am going from then this is going to be pi by 2 and the same copy. Like this. Now, I am doing. Okay. So, now as you can see that f of 0, this is so here f, if I am going from this side approaching 0 from this side, then I am going to get minus pi by 2. So, 0 minus is equal to minus pi by 2. Now, f of 0 plus, I am going from this side to 0. So, I am going to get, I am going from this side. So, I will get pi by 2. And so, it has a jump discontinuity. So, now we have already calculated the Fourier series and Fourier coefficient, then the Fourier series of this function. We have noticed in one of the earlier lecture that the Fourier series of this function is given by n equal to 1 to infinity sin n x by n. This is what we had already seen. Okay. Now, we want to look at the partial sum f n at 0 or f n theta minus f of theta. So, this is equal to summation over n equal to 1 to capital N sin n theta divided by n, and then this is pi minus theta by 2 by the definition, where theta belongs to 0 to 2 pi. So, this let me call this function as g n of theta. Now, if I look at g n prime at theta, this is equal to summation over n equal to 1 to n, and this is going to be cos n theta plus 1 by 2, and let us cos n theta is e to the power I n theta plus e to the power minus I n theta divided by 2. So, therefore, this I can going to write, this is summation over minus n to n not equal to 0 e to the power I n theta and plus 1 by 2 and a factor of 2, and this is nothing but 1 by 2, then this is e to the power I n theta minus 1 to 1, then this is our familiar object, it is half of d n theta. Now, as you can see that the critical point of g n theta, this is going to be when, so critical theta is equal to is n plus 1 half of theta, this is equal to 0, that means this is equal to some k pi. Therefore, the first critical point for g n is theta n, which is equal to pi by, when this k is 1. So, this is n plus 1 half. That is what is our first critical point. Okay. Now, g n theta, by fundamental theorem of calculus, this is equal to 0 to theta g n prime of theta d theta plus g 0 g n of 0. So, therefore, g n of theta n, this is equal to 0 to theta n g n prime, g n prime is nothing but half d n Dirichlet kernel. This is sin n plus 1 half theta by sin theta by 2 d theta plus g n 0 is equal to g n 0 is equal to minus pi by 2. That is what it is. So, now let us compute this integral. Now, let this is a simple thing to compute. If we are making a change of variable, then this, if theta is 0, theta 0, t is equal to 0. When theta is equal to theta n, then t is equal to pi. Therefore, g n theta n is equal to 1 by 2 integral 0 to pi, then this is sin t divided by sin t by 2 times n plus 1 half, and then dt is equal to d theta is equal to dt by n plus 1 half, then this is dt minus pi by 2. And this, as you can see, I can write this as 0 to pi sin t by t into t by 2 into n plus 1 half divided by sin t by 2 into n plus 1 half. I am incorporating this half here, and then this is dt minus pi by 2. As n goes to infinity, then we know that this t by 2 n plus 1 half divided by sin t by 2 times n plus 1 half, this goes to 1. So, now this goes to 0 to pi sin t by t dt minus of pi by 2. Now, this basically this is going to be equal, approximately this is equal to 0.08949 pi. This is approximately this. So, now what does it say? So, which is saying that this is actually there is a 9% of overshoot. It is overshooting the 9% of what we need to get at this. So, if we, what does this mean? So, now we have this graph. So, this is 2 pi and then this is 0, this is minus 2 pi. So, now if we are approximating, that means approximating is what? So, essentially we are talking about the partial sum of the Fourier series. So, now if you take more and more terms of n, capital N, then we are getting closer and closer. So, now wherever there is a jump discontinuity, this is saying that the original function is something like this, what we have, and then this is 0, and then on this side this is going to be, this is the original function. So, now when we are approximating, we are kind of getting on this more and more. If we are taking, we are going to get the smooth function. And then from here you will get the change of, this is the shooting, overshooting this, similarly in this. So, this is overshooting then by 9%. So, this is called this essentially is called the Gibbs phenomena. So, this is very interestingly found that if you take more and more number of terms, then you are overshooting or undershooting by 9% of the actual thing. So, that is this phenomena can occur only at the jump discontinuity. So, this is and this occurs only at the jump discontinuity. So, that means the partial sums overshoots or undershoot f near jump discontinuity. Okay, because there what we have seen that near 0 we should get pi or minus pi. So, near 0 it is on this side, if we are going to get pi, but we are going to get 0.089, that means there is a change in the 9% error. So, that is a phenomena which happens in beautiful phenomena which happens at every jump discontinuity. Thank you.